什么都看不到。OK
OK， 行。
要 off 掉才可以啊，
听一下。
要 off 掉那个。我们之前是
So I just want to do a voice check testing 1 2 3 4. Can you guys hear me?
即将开始。
听得到，我能回房间看一下。看到了，听到了。
It depends on like.
等一下，我先发地址给你。
OK, sure.
只有一次啊，其他的也可以看网络水准。但是网络水准会变，比如说我这个，
应该跟视频没关系的，
我这个它就只能，
然后拿正拿3次，
这个拿3次。
我有可能需要借一个耳机线，我怕我这个样子有点不是好，谢谢。啊，这个已经有了。谢谢。
但是标题是什么？
标题
就是一般算法。
Testing, 1 2 3 4. Testing.
它不用保存的。
你这个是充这个东西，还是充里面的？
外面那个。
所以其实里面的是可以拔掉的。
可以啊，直接可以拔掉。这不用。因为口上没电。你可以直接讲，我们直接听你讲。
OK， 那边没有，就是那个 live 那边 OK 吗？
可以。
And the voice is okay as well. Just want to confirm that it is it's not too, the volume is not too slow. Okay, cool. Okay, guys. So today I'm going to talk about genetic algorithm, and notice for those people who has once written the wrong word and are included, it is genetic algorithm. It's not generic algorithm, because we're talking about genes. We're talking about chromosome here. So previously, I just glanced around on the topics that we cover, and then I realized that Yoga once talked about machine learning before, and he raised a couple of concepts like linear regression, partial derivative, and gradient descent. So all these concepts are very important in machine learning, so on and so forth, but they are a little bit complicated. So the question is, if we don't know anything about these kind of things, can we do machine learning? The answer is, of course, yes. So introducing in genetic algorithm. So what is genetic algorithm? This is a definition I extract from Wikipedia, which says a genetic algorithm is a method for solving both constrained and unconstrained optimization problems that is based on natural selection and the process that drives biological evolution. But I want to give you guys a very different definition, which I think actually matches the true story. You can also regard genetic algorithm as an algorithm that you want to know a good, but not necessarily the best result of the problem, but you don't know how to get it. Or maybe you just suck at algorithms like me, so you just want to have a very generic algorithm so you can implement that without actually knowing how to do it. So today I'm going to give you guys 2 examples. Both of the examples are real experience, in my past real experience. One is my working experience, another one is my final year project, and they both use genetic algorithm to solve the issue. So example number 1, and you can just ignore the fonts. originally this actually was a problem that I need to solve in my past job, and originally it was about fund allocation, about how to allocate the stocks that we that our traders purchase, and that they need to allocate into funds according to a specific ratio. But in order to make it like layman understandable, let's assume we got a couple of robbers, and they have, assuming they have robbed the bank and they got a pile of cash. And of course, as you know, all the bank notes they have different face values. For example, renminbi, it has like $1, $5, $10, $20, $50, and $100. So for some reason, they have agreed on a very strange allocation scheme. That, for example, for robber one, he is entitled to say like 10 banknotes instead of like $10. And for the robber two, he is entitled to like 20 banknotes. And then they realize if they do it in this way, there might be some unfairness, because even if you are entitled to like 100 banknotes, maybe they're all just $1 banknotes. So in the last, you only got $100. So they want to, in addition to the ratio of the banknotes that they agree, but they also want to make it as fair as possible, meaning that after the allocation, they want to make sure that the average face value of the banknotes that they get should be as close as possible. So if we want to look at maths, this is the corresponding mathematical representation, which I don't actually want you to look at because there might be errors in it. I just made it up in the morning. But the only point I want you to look at is if you look at the evaluation function. So this actually means like you got this formula, and you got a couple of free variables, the q1, the j, comma I, this kind of free variables, and you also got a couple of constants. You got a couple of constraints, and you want to find those q, j, comma I, such that this formula gives you the minimal value. What does it mean? It means that as long as you can find a solution of the q's, you definitely can evaluate this function. It's just that you don't know whether the value you get is the minimal or not. So if you look at this, I'm not sorry, I'm not going to do a lot of mathematical analysis on this problem, because this is actually a little bit similar to what Yoga talked about last time. It is related to linear regression. But the different thing is, last time when Yoga talked about the problem, talk about the problem, the points are actually fixated. What we need to figure out is to figure out the slope and what kind of line that we want to use to minimize the distance of the points. But for this time, those points are actually flexible, so meaning that they can move to a couple of places. So there's also, if you look at like assuming, let's talk about a very simple example. So for example, there's only two people, and there are only like say how to say that three. Let's say there's only 6 banknotes, and 3 of them are $1, and 3 of them are $10, for example. And if they agree that they want to divide this loot equally, so 3 notes for each one, then as you know, you cannot actually divide it equally, because you cannot just split the $10 banknotes into half and claim that they're just $5 for each, right? So actually, this problem is very, very simple if we do not have the constraint that the quantity of the banknotes actually need to be integers. So it is linear regression if we actually allow those quantity to be real numbers. But now, because we need to ensure that the solution are actually a bunch of integers, which means that this problem is actually in integer programming question, which is NP hard. But this is actually a very good practice for you guys to practice algorithm if you want to give it a try. But today I'm not talking about that. I'm talking about something else. So how does genetic algorithm give us an answer? So this is a graph that we usually use to denote that how a genetic algorithm views. Imagine no matter whether your solution is fair or not, you can always to make up a solution that actually satisfy the requirement that for each of the robber he got the number of the banknotes that he get, and then all the banknotes are distributed and there's no one left, right? But the tricky thing is, it does not guarantee that the face values, the average face value, are as close as to each other as possible. So, assuming we already got a solution, how can we get the optimal one? So this is the process that we talk about in genetic algorithm. Assuming we have already got a solution at the very beginning, and then we try to mutate the solution. So in this example, what we talk about in this specific example is a little bit special, because usually when people talk about genetic algorithm, they will talk about, like, for all the solution, it can be expressed as 0 ones, right? For example, your solution can be denoted as a 100 bits of data. For each of the bit, you can be 0, it can be 1. And then you use this solution to evaluate the fitness function, and to see whether this is good or not. And then you mutate, and then you get another set of 100 bits of data, and then you can evaluate again. So, but in this example, the mutate function is a little bit different, because if you want to mutate from one solution to another solution, you still need to stick to the constraint in the problem, which means that for each of the robber, they should still the total quantity of the banknotes should be entitled to them should still remain the same, right? But this does not impact how the genetic algorithm works. So you got a bunch of solution here. You mutate that, you got something even more. For example, originally you got like 100 solutions. You mutated that, and you got 10,000 or even 100,000 of solutions. For each of the solution, in the mutants, you can evaluate the fitness of it. In this case, we'll use the very complicated function we just saw, and then for each of the solution, we get a value which indicate the fitness of the solution, right? And then we sort those solutions according to the score. We got like which ones we should keep, which one we should just discard. And then we should keep, for example, just like 10% of the mutants that we just created, and we redo the process until two exit conditions. Either we already found a good enough solution that we are happy about it, or we have a maximum generation count. For example, if we do this process like 10,000 times already, and we don't want to waste time anymore, and we just exit it, and we just pick the best one as we can get. The idea is very simple, right? But the thing is, you got a lot of parameters that you can choose in this genetic algorithm in order to improve your performance. Just like what I said, let's start with the maximum candidate count. This is the original candidate pool that we're talking about. How many candidates we want to keep for each of the generation at the very beginning. And then when you mutate that, you got a lot of different mutation strategy. Mutation strategy is something like, just now I talk about mutation strategy, right? We're talking about assuming we already got a solution. And then, for example, a person A and a person B, both of them have 10 10 $1 bills and 10 $10 bills. And how to get another solution, how to mutate that? It's very simple. I just give another one, sorry, the person A just give a $1 bill to person B, and the person B give a $10 bill to person A. Then we get another solution, right? So this is the very simple mutation strategy. But for other problems, we have another mutation strategy called crossing over. What does it mean? It is trying to imitate the sexual reproduction in biology. So assuming you have two genes as your candidates, you can just randomly just pick some of them from gene A and some of them from gene B, and assuming that, notice this is just an assumption because it will work for some of the problems, it won't work for some other problems, and assuming that these two good genes will give you an even better offsprings. So here we talk about we have different mutation strategies. And of course, we also have we can also change the mutant per candidate. So for example, for one of the candidate, how many mutants do you want to generate from the same candidate? So that you can get so that this can control the mutant pool that we talk about on the bottom left of the picture. And finally, we can also change the mutation intensity. What does it mean? It means that at the very beginning, you can just change a solution to a very different solution randomly because you want to explore the solution. You want to explore the solution plane. But when you're gradually reaching the optimal result of the problem, you actually don't want to do that because you know it's very you know the optimal solution is very near. You just want to search the solution space very near to the candidates that you got. So this is what we call a simulated annealing, meaning that at the very beginning you mutate the candidates very fervently, but at the very end you mutate it at the very you just touch it a little bit and then try to mutate it a little bit. So this is also another strategy we also use. And of course, you can even change the fitness function if the fitness function is not very well defined in your problem regime. So, having said that, let's look at the code a little bit. This is actually my first week writing code. I do this as a practice, and I actually sent this to my friend, and he said I'm writing C# instead of Go. But so I'll just give you a very a picture of what it's talking about. So this is the core part of the algorithm. At the very beginning, we got the solution, right? And this is so-called I get the default solution. Actually, it doesn't really matter as long as it is a valid solution, and it's okay because the generic algorithm will always get us to the right solution. We got the candidate pool. At the very beginning, it's very simple because we only got one solution, so the candidate pool is just that particular solution. And then now we got the for loop. For each for loop, we will do the first step, populating the offspring. In this step, we basically just look at each of the solutions in the candidate pool, and then for each of them, we find out a couple of the mutates, so that we put all the mutants in the mutants in the offspring solution pool. And then the second step, we evaluate each of the solution and sort them. And then after we sort them, we got we know the best of it, and we got a score. If the score is already satisfactory, in this case the score is 0, then we just return the result directly. Or just like what I said, if the generation count is already bigger than our configuration, bigger than the max generation count, and we just return it already. And if the requirement is not met yet, then we will just look at okay, so how many candidates we want in the next round, and also and we'll just populate the candidate solution and looking for the next round. So the general idea of the genetic algorithm is very, very simple. But of course, let's look at the probability of string solution. Depending on the problem, it can be very difficult, or it can be very complex, or it can be very simple. And here what we do is just like what I said, I got the candidates and then I mutate them according to the number of the mutates for each of the candidates. And then I do some reduce duplicate, because it is possible, especially at the very beginning, that you do a lot of mutants and some of the mutants are actually the same. Then it will actually be wasting your performance or wasting your CPU time if you want to calculate the same result again and again. So it's very important to reduce the duplicate for some of the problems. And then after we got the mutants, and we put the mutants out. So this is basically the idea. And then so in the end, I forgot to actually run the program. And I'm actually using Atom. I'm not sure like what kind of IDE you guys are doing, but I just want to do a proxy here because I think it's quite good. Because for Atom, you can actually do something nice, like for example, I want to know the definition of this. Which vendor? Cannot remember. Something like that. This is using the GoDef function. And also, whenever I do a save, this is the Go test, right? We always do the the testing for a Go program. And if we do a save, and it will automatically run the test case to tell you like what is right and what is wrong. And also, it will give you it will use the Go link in Atom automatically. So because now I correct everything at the very beginning, so now there's 0 error, 0 warning. So, but it's very useful, especially when you're actually writing code. So this is the result of the, well, actually I shouldn't use this. I should just use a terminal directly. Where's my terminal? Okay, good. So the test case is very simple. Oh, actually, I need to show the test case as well. Go test, main test here. So here I define the problems and also define the expected solutions here. And the problem I'm going to use is actually this one. What does it say? It says, do a test on this. I'm basically just, this is GA solution, right? Okay. This is the configuration that I use for generally equal to our expected solution. So if I run the terminal, my terminal is hiding again. So actually, what you are seeing here is it will try to calculate for each of the generation, and then to output the score. And the score is what we just talked about, the according to our evaluation function. So you can see the trend, right? At the very beginning, it is 0.48, blah blah, and then at the around generation 5, it start to stabilize, and then all to the end, I think this is the best solution already. So usually, if we in a genetic algorithm, if we found that it is already stabilized, and it usually means that we don't actually need to proceed further, because even if you proceed further, it won't give you a better result anyway. What if we change the parameters? Parameters. So for example, if we actually don't give them that kind of freedom. So this is like for each of the generation, we will just give it like 10 candidates, and then 10 candidates per generation. And for each of the candidate, they can only generate 10 mutants, and this is the result. So you can see that although it also tried to run like 20 generations, And this time it runs pretty fast because you know that the computation, the numbers of computation that this program need to do is significantly lesser. But it doesn't actually get the correct result. So as you can see, the final score is like 0.0000604 instead of the 120 that we just talked about. So this is a very magical configuration because for each of the different genetic algorithm problem, it will actually have a different configuration that actually suit the best. And even if you do the parameter, sometimes it doesn't really actually means that this is the best one. Okay, so this is the first example. And the second example is my, sorry, I need to do a, and the second example is my final year project. It's a, how to say that, it is an automated music generation project. What I try to do is, at the very beginning, I try to, I just got a couple of music from Bach, named the fugues. And then I analyzed the characteristic and just put them into my database. And then with those data in my database, and I try to use stochastic generation to generate songs. So this is actually leads to a introduction document that I on my blog that I was talking about the project. So what I was doing is at the very beginning I tried to chop up the music into chunks and then to analyze the linkage between them. For example, for these two sections, to these two chunks, because for each chunk we can select different kind of elements that we originally we analyzed from Bach. So at the figure 1, we have 4 different kinds of, actually 3 different kinds of chunks that we can select from. And we can also select the different linkage. So for example, from one chunk to another chunk, do we want to offset it by adjacent nodes, or we want to offset that by the first node of the adjacent chunk? And that's the type of the linkage. We can also alter the offset of the linkage. So for example, at the figure 3, we can choose whether the first node can be a D, or can be C, or can be a E, something like that. So if you want to represent all these kind of things, you can just ignore like the notation or something like that. But what I want to say is, for all this kind of music, it can be notated into just a string of the of different data. As long as we got data, we can represent it just like a gene, and then we can do mutation, and then we can evaluate. So all this kind of thing. So why we are using genetic algorithm? Because we have a computation on the search space of like, in order to compose a song, what is the what is search space of this of this kind of thing? And we talk about like 3.7 times 10 to the power 14 different possibility for each of the segment. I'm just talking about a segment because a song is composed of like, I don't know, God knows, like 50 or even more segments. So you know this is a very, very big search space. And we also got a lot of rules because, you know, Bach is from the Baroque period, and there are a lot of different rules on how to make a good piece of music. So those rules are very good evaluation function. But unfortunately, if you want to compose according to those rules, it will be it will actually make your music very boring. We actually tried that before we used genetic algorithm. So we also do not actually need a optimal solution. Even if you look at Bach's original work, it doesn't actually fit the evaluation function very closely. So, but even though that happens, Bach's work still the best music of the world during that time. And also, if you're choosing genetic algorithm, usually if you want to get a very high quantity of the result, it takes time. But fortunately, this is an offline application, and we don't really care about that. Although during that time, I remember the last time we generate a music, something like that, it takes about 1 hour using my laptop. Although my laptop was not with very great configuration, but I guess you can just see the point. So how did we do that? We do it in a very similar approach, just like what I did in the banknote problem. So we got the requirements, we got a generator, we got the 100 candidates. We mutate them for each of the candidates. We got 10 mutants. We evaluate them and we sort them. We got a scoreboard. So we find the best of them to see if the criteria is reached or not. If no, then it just flow back to the next generation as candidates and repeat this process again until we got the solution. So this is basically the idea of the genetic algorithm. And as a bonus, I'll let you guys listen to one of the songs that the program actually generated. Let's see if I can still. No. This is actually a buff one. So because actually we're not recording the song from this computer, I guess. So for those folks that actually looking at this presentation live, then you have to click on your YouTube on your computer. So I guess that's basically it. What I wanted to say as my final word is that genetic algorithm is not something very magical, but it does allow